Yes, sir.
Okay, good evening to all. I hope last week's session, all of you might have gone through the questions and let us understand the areas which you people are looking for more explanation from our end. So these things we will understand from your responses to the questions. So always try to fill the questions and try to ask more questions. During the session also, you can raise your hand and ask a question, or you can come in the audio and ask a question. So which are all will help us to understand which area we should press more and talk more. Because then we will understand the areas of your needs, which will help all of you. Okay, fine. Last week we have almost covered something about the basic forces and basic structural systems, both vertical spanning systems, horizontal spanning systems, things like that. And we have just went up to basic designs, different methods of design. We will go slightly in detail into those, and we will see some of the internationally provided or constructed structures, photographs, and we will try to understand the structural actions in those structures, how they designed and how they are standing in this class. I'll share my screen now so that it will be more helpful for both you as well as to me. I think all these things we have already covered, and we went all the way. We understood what is seismic load, accidental load, what is the different spanning systems, different forces that has been shared by different members, or how the load travels to the foundation from the structure through different actions, axial, bending, shear, torsion, things like that. Is the screen visible to all of you?
Yes, sir.
Visible?
Yes, sir. It's visible.
Okay, okay, fine. So we started discussing on the working stress versus limit state design. The design as such, we mean primarily the structural design, in which we proportion each members in a structural system to carry the expected loads on them. The loads, as we discussed in the last class, may come just by building the structure itself. It will come, it will block the wind, so the wind load will come just by building the structure in a position. If some vibrations travel on the earth, like earthquake or a blast, the structure will generate inertia load within the structure equal to mass into acceleration, F is equal to ma, Newton's law, and thus inertial forces in the structure. So things like that. In addition, when we try to occupy the structure, we generate imposed load or live loads in the structure. Also, there may be moving loads if some vehicles are moving, or some cranes are moving. So these loads will have different magnitudes, different directions. When the load go on changing in magnitude and direction in such a way that the rate of change of load will start affecting the behavior of the structure, then such a load is called dynamic load. Normally, all loads are treated as static loads, even though other than dead load, every other load is a dynamic load. The rate of change of loading is small, so we take them as pseudo-static loads or equivalent static loads. So in such cases, the loading on the structure can be analyzed by treating the loads as a static load, and we can arrive at the corresponding bending moments, live loads, bending moments, shear forces, axial effects like tension, compression, or torsional moments. And then next come the design. Till analysis we have gone. Now, once we do the analysis, we get the forces in the member, and we need to proportion each of these beams, columns, braces, everything to carry corresponding forces that comes in the member in course of the loading in the structure. Now, this process of design has been originally done through allowable stress or working stress method, which we discussed in the last class, wherein out of the failure load in any material, if concrete, if it is FCK, we all know that when you do a compression test in a compression testing machine with a cube of 15 centimeter by 15 centimeter by 15 centimeter, it will fail at a load of maximum peak stress, which if tested on the 28th day, and the load is this load is called converted into a stress and called its characteristic compressive stress or FCK. By characteristic compressive stress, we mean if you test 100 cubes, it is this particular value above which 95% of the or 95 test will fall, and only 5% is expected to fall below. For example, if you take M25 concrete and test 100 cubes, you get 95 cubes above 25 Newton per mm square as the failure stress and 5 cubes below. So then that concrete is called a concrete mix of M25, and its characteristic strength we take as 25 Newton per mm square, FCK value. It doesn't mean that the concrete is exactly having 25 Newton per mm square. 95% of the things will have excess of that value. 5% can fall below. So that is why in the seismic load design we have discussed, we design the structure for a smaller loading, taking into account ductility, overstrength, etc. This overstrength comes from this parameter. We take only 95% passing value, then most 95% of the samples will fall above M25, means it may be M26, 27, 30, 35, like that higher value. 5% will be lower. And then we apply a factor of safety on this FCK value and say this is the allowable stress in the material or working stress in the material, concrete. So we do this for bending, we do this for tension, we do this for compression, direct compression, bending tension, etc. And we treat the concrete as a material which is primarily expected to carry compression only. So we treat the allowable tensile stress in the concrete is always as 0, even though it is not. It can carry certain amount of tension, but we neglect this in the design process. And if you take steel, mild steel, for example, the characteristic compressive stress or tensile stress in mild steel is 250 Newton per millimeter square, as you know, Fe 250 grade of steel. This means if you take 100 samples of that particular steel, 95 will test above 250 Newton per mm square. 5% can go below 250 Newton per mm square. Similarly, if you take Fe 500 TMT bars, which is the normal reinforcing steel all of you see anywhere in a site nowadays, the test should yield 100 tests if we conduct on the same material. Same material means samples from the same lot. So each one once tested will fail and we reject that. Then next. So 100 tests when we conduct, 95% of the test should have a value 500 Newton per mm square or better. And 5% of the samples can have less than 500 Newton per. So such a steel is called characteristic compressive strength 500 Newton per mm square or 500 MPa. So Fe 500 steel. Like that 550 is in the market. And occasionally we get Fe 600 also in the market. Earlier all our steels were Fe 415. Now for availability of 415 is much less. So the common steel that is used everywhere is Fe 500 and Fe 550. 550 is very common nowadays. More the strength, you can use less area of steel. Now we apply a factor of safety on the 500 Newton per mm square and get the allowable stress on the reinforcement bar or working stress on the reinforcement bar, and the calculated tension, compression or bending, whatever limited to the working stress or allowable stress. That method is called working stress design. And if we come down to limit state design, this common approach of applying a single factor of safety on the material strength is modified by splitting the factor of safety into two different sections. Like a part of the factor of safety is applied on the material strength. That is just like we discussed, Fe 250 steel or Fe 500 steel, we apply a part of the factor of safety called partial safety factor in the basic material strength of 500 Newton per mm square, and other part of the factor of safety is used to apply on the loads, so that or the bending moments or the load effects. The load makes different effects. They make bending moment, shear force, they make axial force, they make tension, they make compression. So all these are called load effects. So the load effects is boosted by a safety factor. This is called partial safety factor or load factor. It is called load factor gamma F. If in terms of caudal words, it is gamma F. And what we apply on the material strength is gamma M. So we calculate the strength of the material here. The strength of, if we give an angle ISA 50-56 or an ISMB 200, then we calculate its capacity, bending capacity as the MD, moment design moment. MD stands for design moment. And then compare this with a value of moment calculated from the loads magnified by a load factor gamma F. So this is called the limit state design. In limit state design, we deal with the strength value. In working stress method, we deal with the stress value. Also, the strength part is one part only. The structure can have several other failure effects. Need not fail, but failure effects. Like if you have an excess deflection in a structure, people will find it difficult to stand on the structure or use the structure because it is deflecting. They may be afraid of moving in, as thinking that it may fail. It may not fail. Strength part is all right. It can stand, but still the excess deflection will give the user a feeling that he is standing on an unsafe structure. So the deflection has to be controlled to the satisfaction of the user. So this is called serviceability. The structure should be not only strong enough, but it should be serviceable as well. Another factor is crack. If the structure is excessively cracked, then the user may feel the structure is not strong enough. Even though it is strong enough, we can calculate its strength limit state and prove it is strong. The user should feel it is strong by looking at the structure. So the crack should be controlled, deflection should be controlled, corrosion should be controlled if it is excessively corroded. So all these parameters are serviceability parameters. So there are serviceability, they are called serviceability limit states, in other words. So we should match strength limit state and serviceability limit state. And the load factor that is applied on the loads for each of this is different and hence dealt separately. This yield certain amount of economy in the design compared to working stress design or working stress method or allowable stress method. There was a design method in between. In 1954, Russians introduced limit state design. Till then, everything was working stress method. Now, the limit state method design as a modified factor is used in the ultimate load design used in the Europe at that point of time. Now, every country has changed Euro code and every country code has changed to limit state design. Even though in the changeover path, the working stress design afterwards, some of the countries used a ultimate load design, which was a combination of working stress and a limit state design. And then we define two separate limit states, one for the strength and one for the serviceability, and satisfy both. So that is the limit state design what we do. Okay, now we will come back to our original discussion. First on these are typical tension structures. What you see, you can see the tension structures. These membranes are in pure tension. So all these membranes that is pulled across a structural framework will be always in tension. That shape is a hyperbolic paraboloid. There is a parabola in this direction and a hyperboloid on the other direction. Hyperbola on the other direction, parabola in this direction. A combination of a parabola and a hyperbola is called hyperbolic paraboloid. A certain shell shape, when this is kept in the reverse manner, that is upside down, which we have seen one of the previous slides, this one, it will be in compression. But in this case, this is in pure tension. So when the hyperbola is open, concave upwards or convex downwards, it is in tension. And when it is convex upwards, as we have seen in the previous slide, it is in compression. Now you can see another type of tension structures. All these membrane structures are mostly tensile because tension is a thing that can be carried by wire ropes. When it is compression, you get an additional strength limiting factor called buckling. Actually, these are in compression. In this case, these pillars are in compression, but every other element, these all the ties from the pillars, the surface, everything is in tension. So this is the tensile fabric roofing. This is a dome that is made in London to commemorate the 21st century, that is year 2000, January 1st. So it's a big thing, big in size. So it's a pure tension structure. Now you can see the London Olympic Stadium, 2012 London Olympic Stadium. You see, it is again another tension structure. Every element is made. There are certain compression members, but basically it's a opened out view of the stadium roof. It was also a purely tensile structure. You can see the 2008 Beijing Olympic Stadium here called Bird's Nest. Bird's Nest. You can see this is also an element that is again a membrane or a shell shape, but using the portal frames. These are all a combination of huge number of portal frames running, one like that, one like this. You might have seen some weaving of elements to generate shapes, just like some woven chairs and all. Here, each one of this is a portal frame. You can see the basic shapes of the portal frame in this plan. See, each one is a portal frame on that grid. So each grid, each column originates two portal frames supported on that. And the combination of that portal frame gives us a huge stadium with a roof shape of that elliptical sheet. Now you can see the portals that is used in this stadium. Typically a bottom hinged portal, both portals. One is a concave portal and a convex portal, a combination of which is made here. And this is basically steel. And the dimensions is huge, like 200 meter, 300 meter. It is not small. 200, 300 meter long and huge sizes. You can see a close-up view of that. You can see a photo in which that leg element with sizes of some of the people standing there, huge sizes like that. So you were seeing this part of the leg, which is a plated box. This is a plated box. This is 4-plate box. Inside is hollow. So such huge steel shell elements is the leg of that portal, which has to span across 200, 300 meters across the stadium to give you a nice view from inside the stadium. You are again seeing an overall picture of the stadium, and these are the elements, a long view of the elements, which on close-up you have seen shape, and the close-up of the element is almost 1 meter or so in each direction, 1 meter by 1 meter square boxes running, and the bracing member also the same sizes running horizontally and vertically, and then forms the portal. Okay, now we are looking at a structure which is again another Chinese structure. It is Beijing Television Broadcast Office Tower in Beijing, China. The height is around 70 stories. After climbing all the way up to 70 stories, the structure starts taking a bend, and to match another 70-story tower, another leg of 70-story. Each one is all office spaces, huge sizes inside, all office spaces inside. So it has to stand against wind, earthquake, all with this odd shape. You can imagine. So such are the shapes that you build internationally. So we should be able to analyze them. We should be able to proportion them. These are the things that is visioned from the architects or other visionaries who look at, artists who look at the structure, and they give some preliminary sketches, and we engineers are to come up with solutions which can keep the thing for its lifetime, maybe 100 years or 150 years, without any issues, with all the loadings, earthquakes or cyclones, whatever that can happen during this time. We are not expecting the people inside, the life of the people inside to get affected, or the wealth that is stored inside to get affected during such an earthquake or a cyclone. So we have discussed the theory of earthquake resistant design in the last class. So we know there are different type of earthquake. There may be area where moderate, minor earthquakes are there, moderate earthquakes are there. In all these cases, minor earthquakes should not be felt or should not be creating any problem with the structure. Whereas moderate earthquakes can create some damage, but of course repairable. And in a major earthquake, which is expected only once in the lifetime of the structure, which is expected to repeat maybe once in 500 years or once in 2000 years, which is the most maximum considered earthquake, in other terms, should not collapse the structure. Under such a earthquake coming in the lifetime of 150 years of the structure should be collapse prevented by its structural system. So there we utilize the ductility, there we utilize the overstrength and all the redundancy, everything. So you get another view of the same tower. You can see from the other angle. The earlier we have seen it from the opposite side. Now you can see it from the other angle. This is facing a main highway. You can see the highway running there. It's a real photograph. You can go through the Google or other search engines to identify more pictures. Now coming to bridges. Bridges are a totally different structural systems, always handling moving and dynamic loads. Dynamic loads, as we defined already, that the loads whose rate of change of magnitude or direction will be so fast that that rate of change will induce behavioral changes in the structure, structural behavior. So these are earlier times when steel was not detected or used in construction. We had only compression, only structural systems and structural elements. So these are the arches of almost AD 600, which is almost 1400 or 1500 years back. Steel was not a common material for construction. So they used to make structural systems which always carry compression. So if we load this, it is always in compression because it is an arch. You can see another view of same bridge, which is again similar bridge, which is again in arch. So when it is loaded with vehicles or people on the top, the arch will be compression subjected to a compression. We have seen in the last class how an arch carry the loads to the foundation. Now the bridges can be different types. There can be steel arch bridges. There can be steel truss bridges. Then there can be concrete beams, concrete arches, masonry arches, which we have seen just now, pre-stressed concrete beam bridges, which are the most common bridges nowadays. Most of the bridges that you see can be categorized into this category or this category. RCC beams, beam and slab bridges, or pre-stressed concrete beam and slab bridge. Then there can be cable stayed bridges, there can be suspension bridges. All these things you might have covered in your right from your applied mechanics, strength of materials, analysis of structures. Everywhere these structures are covered. So I'm not going in detail into that, but we will see some of the images of or magnitudes of such a structure. This is 1800 meter span cable stayed bridge called Stonecutters Bridge at Hong Kong, which is now completed. It was under compression when the slide was made earlier, wherein huge ships are passing below. This is in Hong Kong port, and the ships that pass underneath. So you need a very high headroom and very large span with a very bad soil and the waterway here to go and do a foundation. So the engineers thought of keeping the foundation on the land far away places and then bridge them using a technology called cable stayed bridges. The deck of the bridge, which is a beam, is tied back with cables to a tower, and this is balanced by ties to the other side. So this is a cable stayed deck. So that is why it is called a cable stayed bridge. Suspension bridge is slightly different. If it is a suspension bridge, you will get a suspension rope, a parabolic rope here. But in cable stayed bridges, there is no suspension cables. The cables are directly anchored to the deck itself. In the case of suspension bridges, the cable will run from one end to the top of tower, then from top of tower to the other tower with a parabolic shape, then back to the anchor. Then there will be vertical suspenders suspending the deck. But see, the difference in cable stayed is the cable starts from the tower and directly anchor back into the deck. There is no separate transfer through a cable, suspension cable. You can see a close-up view of that one on the bridge shape. So there are a large number of cables logged at almost equal intervals, and then each one is tied back to the tower and it is balanced by cables from the other side. So it's a balanced suspension bridge. There are suspension bridges which is not balanced from tied one side also. You can search for images of the suspension bridges in web and identify different type of suspension bridges. This is the cross section of that bridge. The same bridge what you have seen here. If you take a cross section of this deck, you will see two steel decks, one here and one here, with area for a wind passage in between, so that the horizontal wind, which is the most critical loading in this case, will have a very smooth aerodynamic shape from the cross section, so that wind will affect the minimum in this bridge. Because to span across 1 kilometer vertically for the self weight, you get cables at every 50 meter or 30 meter interval. So it is easy. But for the horizontal load of the wind load, you don't get any support in between the towers. If the towers are 1 kilometer away, your span is 1 kilometer. And for WL square by 8 or whatever your bending moment theory, 1 kilometer you yield huge bending moments. And that has to be taken by in such a horizontal load, the depth of the structure is horizontally measuring from this end to this end, like that. And you can see the vertical load supporting cables here and here, both ends, running to the tower. Probably you are anchored directly onto the deck. These are the cables which we see here. Each of this cable is anchored on two sides of the deck, one here and one here. And on the deck, you have different tracks, vehicles traveling on each direction. And then, of course, there are sometimes cycle tracks and things like that. Okay, this is rather a suspension bridge, not a cable stayed bridge. A suspension, you can think of the size of the cable for such large spans like 1 kilometer or something. When the span is more, suspension bridges are ideal. Suspension bridges touch almost 2.5 kilometers of span nowadays. Large suspension bridges. So you can see it's a cluster of a large number of suspenders tied together or woven together, acting as one cable. This is a suspension bridge under construction. So you can see the suspension bridge and the cable stayed bridge, the two things, one above and one below, different type of cable arrangement. The first one is a suspension bridge. Everything is a wind sensitive structure. So mostly we design them by a wind tunnel test. Wind tunnel test, we make a scale model of the structure, put it in a tunnel, small tunnel, which may be of the size of a room, like 3 meter height and 3 meter width, or 10 meter height and 10 meter width, like that. And then apply the equivalent wind loads of the nature hurricanes or cyclones with the help of mechanical systems like fans and things like that. And when the wind is blown, we will understand the behavior of the structure. So all such vibrations are possible in case of such wind sensitive structures. Now you can see in the case of suspension bridge, the cable runs from one tower to the next tower, and then suspenders go from the cable to the deck. In the case of cable stayed bridge, cables run directly to the deck and there is no suspension cable above. All the cables will start from the tower and end on the deck. Here, only major cable is there. Cable will run from one tower to the other tower and then to the anchorage. And there are suspenders that is running from the, you might have all gone through a recent news of Morbi bridge failure in Gujarat, a suspension bridge failure. You all might have seen the videos as well. That was a suspension bridge. So the main cable was broken and the suspenders cannot yield then, you stand then. So everything fell down into the river. Okay, here you can see these towers are two independent towers tied at the top, but there can be towers like A towers. See, same tower meeting at the top. So there are several different wind parameters and wind patterns which we can utilize for this. Now you can see this is a bridge called Tacoma Narrows, a suspension bridge, which this is a video. Probably you can search for this wording in the web and you will get this video. This is the only bridge that has videographed during a real failure. This bridge was subjected to a normal loading, not an abnormal loading, no cyclones or anything, usual loading, and then started vibrating. And this aerodynamic flutter becoming a huge big vibration, causing final failure of the bridge into the river. So this video is freely available on the net. You can search for that. This is that video, but I am not able to run it today for some technical reason in my system. So probably in some other time I'll show you the video also, or you can all easy to find it in the web. You go and search for Tacoma Narrows Bridge USA. So it failed, and then they rebuilt it in the same shape. Now it is still there. So that is only bridge in which it was videographed by a video shop, photographic shop who was very near to this bridge. That shop was very near to bridge. They photographed, videographed it, and now it is available on the web also. Now coming to the different type of structures, all of you might be familiar with flyers. This is the photograph of the Singapore flyer. You can see it is like a large cycle wheel with spikes in between. All of them are tension members, just like your bicycle. Your bicycles also, from the wheels, from the center axle to the rim, you get very small steel rods, thin dia. They don't carry compression. When you sit on that, actually they are subjected to tension, because if you apply a compression on such thin member, it will start buckling immediately. So the behavior is such that the arch of the wheel, rim of the wheel, will carry primary compression, and then this other members, the spikes that is on the bottom side of the horizontal line, will carry as a tension back to the axle and then directly to the foundation. So that is a rotating flyer. There are small cubicles here wherein people go in and see from when it is rotating from that top to every side of the city easily. This is the, you can see one cubicle in a close-up view. See people sitting inside, and such a heights you can see the other buildings and all those things, far away places. You can see the foundation of that legs is a hinge. You always used to provide hinges in the analysis, portal frame, bottom hinge, bottom fix, but in reality you may not see a hinge normally, because in this part of the country, India, we don't use to make a hinge, even though we assume a hinge in the design analysis. But there are areas, in several areas in the world where they assume a hinge in the structure analysis, they make the hinge in reality. So its bottom point, this point which I am showing you is this area. That photograph is of the bottom part of this vertical column. Bottom is hinged. They are hinged for several things. One, any support settlement or deflection behavior to avoid excessive moments. Also to make sure your analysis, design, assumptions in the analysis, design and construction match with. This is very important, that when you assume a hinge in your analysis, your design should be for a hinge, your drawing should be for a hinge, and your construction should be a hinge. Otherwise, the bending moments and shear forces what you calculate may not have any significance when you really build them. The basic assumptions of boundary conditions of the structure, hinged, fixed, spring, all these things are to be realized at site and constructed accordingly. Otherwise, the analysis is totally useless and of null value. So you can think of the hinge in the bottom of the structure, huge structure. Now you can see this is another photograph which are temporary retaining walls. In construction, temporary retaining walls are very important. They are called sheet pile walls. You can see this is used for underwater construction, coffer dams you call it otherwise. See, this is a locking system with small sheet piles of V shape or U shape. You can see it goes all around, and this is the sea. This is the Hong Kong Sea coming very close to the structure, and we are digging almost 5 to 6 meters below the sea level. The people who work here is around 5 to 6 meters below the sea level. So they protect the seawater coming in to work in this foundation by providing a temporary wall, temporary caisson or temporary sheet pile wall. And to prevent its collapse, they use strutting inside, diagonal strutting, cross strutting, things like that. Now, when we discuss about the construction, the different type of constructions are there. One is cast in place construction, which you saw everywhere. Cast in situ, you call it, or cast in place. That where the construction concrete goes into the final position and then it is placed. You can have precast construction as well. In In bridges and all, you will see it generally, and buildings also it is very common, but of course in Kerala it is not that common. But if you go to Tamil Nadu or Andhra Pradesh, it is very common. The precast buildings. You can search again Google and identify the precasting photographs and see them. So in the precasting technology, you cast it elsewhere, bring it through a transport system, and then assemble it at site. In slip forming, another methodology, you go on having one set of formwork which will be slipping up in a column or a chimney as the construction progresses. This shutter is not removed. It will be slowly moving upwards as you cast the part. The set concrete will be below, and then as you construct more and more, this form will slip up or jump up. If it is jumping up in steps, it is called a jump form. It is slowly slipping continuously, it is called a slip forming. So the progress or the speed will be almost 2 slabs per week and things like that. 2 slabs means 2 floor levels. 1 floor level is itself will take huge time, but in slip forming, these levels are possible. You can see another close-up photograph of the pre-assembled reinforcement cage placed in position. This is the leg of a crane. So a pre-assembled cage put in construction position. The modern materials in concrete, now it is very common that you have self-compacting concrete or a self-leveling concrete. You just make the formwork around and pour the concrete. You don't have to vibrate them because it is self-compacting. You don't have to level it because it is self-leveling. So all these things might be there in your concrete technology, but the making them, this concrete, theoretically we can study in books, but making them is an art rather than a science. So to make so many trials before you can realize them at site, a self-compacting or self-leveling concrete. Now you can see a fiber reinforced concrete. They used for concrete, they used for plaster. Nowadays, what we called ultra high strength concrete is available, M100 and better. Ultra high strength concrete, M100 and better. So all these things are made by use of fibers. There are small fibers that is mixed with the concrete, which will prevent the cracks. It will make the concrete tensile strength higher, and we can make use of that tensile strength also. Now coming to high strength concrete, there are concrete which now available up to 200 Newton per mm square, which is we talk about M20, M30, this is M200. So huge values. So they are required for building such huge structures as well. And think of this 200, comparing it with the normal mild steel reinforcement, where the reinforcement strength or the structural steel strength, your I-beams and all, M250 equivalent or 250 MBA is their strength. And we make concrete to the tune of 200 Newton per mm square. So there's a huge difference in the concrete. Now coming to high strength reinforcing materials, we have carbon fiber reinforcement material. Carbon fiber is a material which is almost 6 to 7 times stronger than your steel. So if your steel is 500 Newton per mm square, the carbon fiber is 3000 Newton per mm square, huge. They are available in reinforcement rod shape. They are available in fabric shape. They are available in laminates. So the basic advantage is that if we use them underwater construction, sea construction and all, there is no corrosion for them. Carbon is a material, inert material. It will not corrode. But for the reinforcement bar, our primary problem is a corrosion. If you have a less cover, if you have a bad quality concrete, you will get corrosion immediately. But for carbon fiber, the advantage is that you will not get any corrosion. They are all stable. And high strength along with the corrosion proof help us to make very, very challenging structures with them. There are stainless steel reinforcement bars also in the market. There are IS code for that, for stainless steel reinforcement bars. So you can use these IS codes for designing them. But of course, for carbon fiber, at the moment, there is no IS code, only in the making condition. They will come in soon. Now we will have to resort to some Euro codes or something to design them. Coming to carbon fiber composites. Now, another form of carbon is also now coming into the research laboratories, which is not yet into the. These are all coming in the sites itself, widely used in the sites. The carbon composite fabrics, which is used to strengthen the elements, which is used to reinforce, to retrofit. If you find a slab is weak, if you find a beam is weak, you can paste these fibers, which are huge strength. So to protect or give them additional strength. So carbon fiber composite. Now, what is called a graphite, a different material. Again, a form of carbon. It is made from graphite, which is having almost 1,000 times stronger than steel. Huge strength. But it is still not in the form of ready to use in industry. It is still in a laboratory product. I think it is 9. I already passed 9. Shall we continue, or I think next class?
Sir, next class.
Pardon?
Next class is fine, sir.
Okay, all right. I think they will have their regular work as well. It will be too much for them if we take extra time on these things. It should go in a normal space rather than a fast space, I think. Okay, so I'll meet them in the next class.
So, anyone have any questions?
Yeah, please.
Good evening, sir.
Yeah, please come in.
Sir, how should we make amphibious structures seismic resistant? How can we make?
See, seismic resistivity, as we discussed in the previous class, comes from basically its mass. One is mass, two ductility. So if the structure's mass is minimal, naturally the inertia force generated in them is a minimal thing. Another method of making them seismic proof is by isolating them from the ground. Means on the ground there is a waveform of energy traveling on the ground. This is called seismic waves. And we isolate our structure with the help of what is called seismic isolators. Just like you are putting a rubber pad. For example, I will explain it. You might be seeing your washing machines vibrating in a large way when its dryers are used. When we used to dryer for drying the cloths, at some point of time, at some velocity, in some speed, RPM, in which the speed of the dryer match with our natural frequency of the machine will start vibrating with a high amplitude. You might have noticed, or several others might have noticed. So how we control this? We insert certain rubber parts below the base of the machine so that the vibration can be reduced, absorbed, and reduced. Just like that, if you have a building or a structure, as you discussed, the amphibious structure or any other structure, they can be isolated from the vibration by inserting certain mediums of isolators in between your structure foundation and the base ground. Probably it will be easy for you to understand by looking at a image or a video, which I'll try to share with you in the next class, so that it will be more clear for all of you to understand at this point. I think we will go with some videos and images in the next class for you to understand. Okay.
Okay,
Yes,
sir, thank you.
Okay.
Anyone
what
else?
comes next?
Anyone else have any doubt?
As we discussed, please all of you come out, no problem. All of us sitting here are all your same age is your same college, same batches. So nobody will think, see, unless you ask, you will not learn. So the first point of learning is that you should sit with your empty hands or empty mind and ready to ask questions, so that whatever coming in, you should be able to absorb to your brains. So unless you ask, you will not get. I may not be knowing your exact question, what is expect, what you are looking at. So we will understand only when you ask something. And probably I also may not be thought of something. When you ask only, I will be thinking of that. So always try to ask questions. Don't afraid of asking questions. Just come out with your questions. You may think it may be stupid, but it may not be stupid question. It may have several value for that question. Any other question? Don't think your questions will be simple or not touching the reality. Imaginary questions, all these things will open up the discussion into the things which you really require. When you come out of the institutes, academics into the field, you may be finding that your 4-year theory classes have to be supported with another 4 years of field experience for you to become a perfect civil engineer. So such questions from your end will help us and help you to go into such practical things rather than the academics or theory you study inside the classrooms. Okay, I hope next class you all will come out with questions, each one with one question at least. You can ask anything on the structural engineering. Even if I don't know, I'll tell you that I'll study this and get back to you so that you and me will study together. So I think we will close.
Yes,
Go
sir.
for the
We'll
next class.
close.
Yeah.
Yes,
Okay.
sir. We'll meet in the next
Okay,
class.
fine.
Thanks.
Thank you
Thank
all.
you. Thank you for joining.
Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you.